Okay, here's what we've been doing all along. In the complex number system, every nth degree polynomial has precisely n zeros. That is exactly what we've been doing. We've been adding everything up to the degree. And this is known as the fundamental theorem of algebra. So congratulations, you've made it to the end of algebra. In complex number system, every nth degree polynomial also has precisely n linear factors, and we've been doing that as well, so there shouldn't be anything new. Finding the zeros of this polynomial. First thing I'm going to do is this one actually looks like it might be factorable, so let's try that. If I do this and make my groups, let's see, I have an x squared in common, take that out. Left with x plus 4. These have a positive 9 in common, x plus 4. Okay. I'm going to bring my two outsiders together, x squared plus 9 and x plus 4 make up this polynomial. And to find the zeros, I have to set my factors equal to 0 and solve them. This one's easy. It's x equals negative 4. This one, on the other hand, I'm going to subtract 9. X squared equals negative 9. So x equals the positive negative square root of negative 9, which is positive negative 3i. So I know I wasn't done from negative 4. I was looking for 2 more zeros because I had a third degree polynomial. And now I have found all 3. Another way to ask the same thing is write that polynomial as a product of linear factors. Well, if you find your zeros, you can turn all your zeros into factors. So let's see what we can do with this. I can't factor by grouping. Maybe I'm going to start with my calculator on this one. Here's what the graph of this function looks like. And I knew to go way up on my y-axis because my y-intercept is positive 54. So this function comes up through, hopefully negative 3 is a good one, comes back down, crosses my y-axis at 54, comes back down. Maybe this is a 0 here. We're going to test that. If I hit trace, I can see, if I hit trace and I put in negative 3, and that gives me y equals 0. So for a fact, I know that one of my zeros happens at negative 3. And then let's test 3, positive 3. It does say 0. So I know x equals 3 twice, because it's a bounce, are also zeros. So here I have found 3 zeros, and I'm looking for a total of 5. Okay, I'm going to take these 3, I'm going to write them as factors, and then I'm going to divide them out. So my factors are x plus 3, that's for that one, and then I'm going to have x minus 3 and x minus 3 for my other two. Okay, instead of doing my division 3 times, I'm going to put all these together into one polynomial and then do my division once. I'm going to FOIL these two together first. This is going to make x squared plus 9, right? Nope, sorry. Let's try that again. This is going to make x squared minus 6x. Oh, I know what I was going to do. I was going to multiply these two together first because my outer and my inner will cancel each other out. So let's get rid of that. This is going to make x squared minus 3x plus 3x cancels each other out, minus 9. Now I only have to multiply that by x minus 3, and that's going to give me x cubed minus 3x squared minus 9x plus 27. And I'm going to divide that out of my original polynomial. I'll have to start a new page for that. Okay, here's my original problem, and we're going to start with some long division. I'm going to have x squared times x cubed, x to the 5th, and keep multiplying that x squared down. It's going to give me negative 3x to the 4th, negative 9x cubed, and positive 27x squared. And I have to go through and change all my signs. and combine. This falls out. Oh, that's convenient. This falls out. 2x cubed minus 26x squared minus 18x plus 54. Now to get a 2x cubed, all I need is a positive 2 up here. 2x cubed minus 6x squared minus 18x plus 27. Nope, 27 times 2 would be 54. Okay, change my signs. Everything should cancel because these were all zeros. Cancel, 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 remainder of 0. So my factors for this problem are x minus 3, x minus 3, that one happened twice. X plus 3 happened once. Lastly, I have x squared plus 2. Now, our directions told us to find the linear factorization, so I still have to break this one down. Well, what are the solutions that come out of this? X squared plus 2 equals 0, means x squared equals negative 2, means x equals plus or minus square root of negative 2, which means x equals positive negative I square roots of 2. I'm going to write those as factors. So that breaks down into x plus I square roots of 2, x minus I square roots of 2. So bring the rest down, and you have your complete factorization. Okay, a little bit more about complex. If a plus bi is a 0 of the function, then the conjugate, a minus bi, is also a 0 of the function. So this is saying if they give you 4 plus 3i, you have to automatically know that 4 minus 3i is also a factor. Your imaginary factors only come in pairs. So let's use that information. Find a 4th degree polynomial, so I'm looking for 4 factors, with real coefficients, that's just standard, with roots of negative 2, so that's going to be x plus 2 as a factor, negative 2 again, x plus 2 as a factor, and negative 2i. Well, if negative 2i is a 0, so that's x plus 2i. I also know that 2i is a 0, so x minus 2i is also a factor. Now, how do I write the polynomial? I multiply all of this together. Take these together first, x squared plus 4x plus 4. If I take these together, x, my inner and my outers are going to fall out, giving me negative 4i squared. We know I squared is negative 1, so this is just, x squared. X squared plus 4. This stays the same. And we're going to do all of our multiplying. I'm going to use the box method to multiply. So I'm going to put my shorter one on the side here. This gives me x to the 4th, 4x cubed, 4x squared, 4x squared, 16x, and 16. Polynomial that comes out of this, x to the 4th, and plus 4x cubed. This is x squared and x squared, so 8x squared, plus 16x plus 16. If I wanted to check this, I could check, and I better see a bounce at x equals negative 2, and then no other x-intercepts because the other two are imaginary.